So now that we know how to do confidence intervals for means, hypothesis testing will be very similar. Again, we've already done hypothesis testing for proportions, and the steps are almost identical. So I'm going to point out to you a lot of the differences, whereas most of the things are the same. So we're still going to check our conditions, and the conditions are going to be the same as the confidence intervals for means we just did. And the only difference between means and proportions is that we use nearly normal instead of success-fail. Then the model, again, is not normal, it's the student's t-model. The test is a one-sample t-test or a one-sample t-interval if you're creating an interval. Then we're going to write our hypotheses, and that again is the same process that we went through. So if you need a little bit of extra help on how to write hypotheses, go back to the video labeled hypotheses in last week's video notes. This week it's going to be the same. My null hypothesis is always going to be equal, but notice here I'm using mu. Mu tells me that it's a means question, whereas previously I used p for a proportions question. Everything else is the same. The alternative hypothesis again is going to be one of these three options, but again I'm using mu. And remember that the hypothesized value is the same for the null and the alternative. We can draw a curve to depict the model, but it's not necessary. Again, sometimes it's helpful to draw the curve in order to figure out what's happening in the alternative hypothesis. Then I'm going to either find the standard error to whatever number of places we're asked, and then use that in the t-score. And notice the t-score formula is still observed minus expected over the standard error, which is what we did before. But for t, observed is the mean that I find, my sample mean, minus the expected, which is the population mean, divided by the standard error, which is the standard deviation of my sample divided by the square root of n. So I typically just do it all together, and this shows you how to break it into two parts. If you do break it into two parts, just like you did for proportions, make sure that this is to 3 or 4 places. Don't ever go to 2 places or you're probably going to regret it. Then the conclusion is exactly the same. I'm finding a p-value. I'm finding the probability that the event could occur, or one more extreme, assuming that the null hypothesis is true. And therefore, if that p-value is very low, then it's not going to happen very often on its own just by random sampling. And therefore, I reject the null. There's probably something wrong with the null hypothesis. Therefore, the alternative is probably true. And again, we'll talk about the wording again when we go through it. And if the p-value is very large, then it happens all of the time based on random sampling, and therefore I fail to reject the null. We're saying the null hypothesis is probably true. So let's take a look at an example. And again, we already did this example in the last video when we looked at a confidence interval. So now I want to test a hypothesis for this. So notice it's the same data, and I'm asking, does this data show a significant difference compared to the 55-point average that we've had in the past 5 seasons? So I've just listed the conditions again, and I'm not going to go through them step by step because I did in the last video. But remember, this is the part I would do in StatCrunch to check the nearly normal condition. So either the histogram is fairly unimodal and symmetric, or this probability plot says it's okay. So again, if you need those conditions in more detail, go back to the video just before this one where we talked about confidence intervals and did this exact same question. So let's look at the hypotheses. Again, everything is context-based, and that makes it difficult for a lot of students. So I'm asking, does this data show a significant difference? So it's not saying, is this more than I would expect from the 55? Is this less than I expect? I'm saying, is this a significant difference, which means my alternative should be a not equal to, because we're saying however far on either side, statistically significant on either side. And what am I expecting to have happen? Remember, my null always says that nothing has changed. So if the average has been 55, I assume it's going to keep being 55. Notice I have not even found this average yet because I don't need to. So I'm going to write my hypotheses not based on what I know from my sample, but based on what I know from the past. So my null hypothesis is that mu is equal to 55, meaning the mean number of points of a high school team scores is equal to 55. The alternative, again, should be not equal to because we're looking for a difference, something different than 55. Now again, I have to do some calculations within StatCrunch, but I want to focus on the part that's different for testing than it was for the confidence interval we just did. So in the last video, I took you through how to do this in StatCrunch, and I'll show you again in a few moments. But this is the output. This is just my summary stats of my data, and the information I'm interested in is the mean, the standard deviation, and of course n, which I already knew to be 10. My calculations is just kind of like the z-score formula, except in the z-score formula I just used different symbols because I was talking about p for proportions. So here I'm saying this is my observed, so notice the 57.8 is going first because that's observed. The 55 is what I expected, and that's mu. The standard deviation, I rounded to 3 places, so again round to 3 or 4, and then take it divided by the square root of 10 because that's the square root of n. So this is the standard deviation of my sample, and then divided by the square root of n. So again, we should be familiar with all of that. We're just doing it a little bit differently than we did last week, because last week we had PQ over n. Side note, this answer, whatever happens down here, should be pretty much equal to this. So it's okay to use that to check. But if you just write this number down here, you're not going to get all of your points. So make sure that you're showing the whole process. Now what I need to do from here is this is a t-score. It's just like my z-score. So we haven't done this yet, but I'm going to show you a screenshot of it on this slide, and then I'll actually take you through the process on the next slide. But what I want to do is I want to go to Stat, Calculators, and T. So previously we went to Stat, Calculators, Normal. I went to Stat, Calculators, T. I have to change my degrees of freedom to 9, and remember 9 comes from that n is 10, and my degrees of freedom is always n minus 1, and 10 minus 1 is 9. So I have 9 degrees of freedom. And what I'm going to do then is I'm going to put my my t-score of 1.472. And again, on the last one, we were saying a significant difference. So be careful here. This is going to be a two-tailed test. Why is it two-tailed? Because we're saying, is it very far below the 55 or is it very far above the 55? And remember, when we do that, we're going to take whatever our score is, and we're going to make it whatever is more extreme. So this is the score of 1.472, and we're saying let's find this area to the right of that, which is this. But because it's a two-tailed test, it would be the same as me taking negative 1.472, somewhere in here. That was not right. Negative 1.472. And then finding this area to the left. So really what I'm going to do is I'm going to take this number times 2 because that would get both tails. So again, the probability that the mean is not equal to 55 is equal to 2 times the probability that t is greater than 1.472. So I took 2 times that answer to get 1.1751. Just as a reminder, remember that this number, your p-value, is a probability. So if I got a number greater than 1, then it's wrong. So if I would have, say, found the area to this side of 1.472 and then doubled it, that would have been greater than 1, and I would have been absolutely wrong. So just always do that check. Then of course I want to talk about my conclusion. And Notice that I wrote the conclusion all together. And so again, if you didn't watch the last video, you should watch that before you do this one. But I included, this was my confidence interval I found in the last video. So this is a full conclusion. So I'm saying with a p-value of 0.1751, which is larger than alpha of 5%, I failed to reject the null hypothesis. There is insufficient evidence to say that the alternative is true. And what's the alternative? That the mean of high school basketball team scores is different than 55. So this is always the alternative hypothesis. I am 90% confident that the true mean average is between 54.31 and 61.29 points. And again, 55 is in here, and therefore it's okay. We're saying that supports failing to reject as 55 falls in the interval. You should not say things like, well, 55 is in the interval, but it's really close to the outside, so we're not sure. That's not how it works. We're saying we're 90% confident that the true value is between the two answers that I've given you, 54.31 and 61.29. So I also want to show you how to do this in StatCrunch, the whole thing, so without having to do it by hand. But before I do that, just in case the screenshots on the last slide weren't enough to help you, real quick, I went to Stat, Summary Stats and Columns to find the mean and standard deviation of my basketball scores. That's where I got that 57.8 and the 6.014. And then if I went to Stat Calculators T, chose 9 degrees of freedom because 10 minus 1 is 9, and plugged in the t-score that I had, 1.472, and found the area to the right, that's where I got the 0.08755 that I took times 2 to make it two-tailed. But now let's just use StatCrunch to actually do the test. Now, why is it helpful? Because a lot of times students forget to take the answer times 2 in a two-tailed test. So when I do this in StatCrunch, it's going to give me my p-value, and notice the two are not going to match up. So if I go to Stat, T-stats, so remember last week we did proportion stats, T-stats is what I did on the last video when I was looking at a confidence interval for means. I have one sample, and I actually have data because I have a column of data called basketball scores, and I'm going to choose that data, and I'm going to do a hypothesis test. And remember, this is the number that I expect. So I was expecting 55, an average of 55 points. Then I'm going to choose the appropriate alternative hypothesis. In this case, not equal to was correct. And then just click compute. And notice I get 0.1751. If I compare this 0.1751 to this answer down here, that tells me I did something wrong, so that should hopefully help me to remember that I have to take this times 2 since it's two-tailed, because the correct answer is the 0.1751. So let's look at this example. If you did watch the last video, we already checked the conditions for this question that had to do with battery lifespan. And so we're not going to check those conditions again. Just go back and look at the last video. What I'd like you to do is perform a hypothesis test to determine if the mean battery life exceeds the 300-minute goal. So this should help you determine your alternative hypothesis. And then again, we're using these 12 values. So go ahead and try the test by hand, check your test in StatCrunch, and then write a conclusion. And then press play. So again, I'm not checking the conditions again because we already did it, but let's take a look at how the rest of it would look. So the hypothesis, remember the null hypothesis is that nothing has changed. And so the goal was 300 minutes. And I'm going to assume that nothing has changed, that my mean battery life is still 300 minutes. The question says determine if the mean battery lifespan exceeds the 300-minute goal. So notice I'm using that to say, well, I want to know if it's statistically greater than 300 based on my sample. So again, in words, the mean battery life is greater than 300 minutes. That's my hypotheses. My calculations, I'm going to find a t-score. The t-score uses the mean of this, and again, I did this in StatCrunch on the previous question, and I just didn't have room to put it on the slide. The mean, according to StatCrunch, was 306.25, and the standard deviation, according to StatCrunch, was 29.31. And that's all I did, is use those values down here. So I did 306.25 and 29.31. 12 comes from the fact that there were 12 batteries, so that's N. And remember, this value is always whatever my hypothesized value is, in this case 300. I do all of that in my calculator, and I come up with 0.7387. So first, I have to find the answer in StatCrunch. So this is not verifying, this is just finding it. When I find the value in StatCrunch, I use 11 degrees of freedom because we have 12 items and 12 minus 1 is 11. And I'm putting the 0.7387 in here and finding the area greater than that because I used greater than here. And I get an answer of 0.23777793. So I just rounded to 4 places. That's my probability. That's my p-value. My p-value happens to be greater than alpha, so I should know right off the bat I'm failing to reject the null. This is where I verify. So you'll always get a question in your assessments to say verify your results. So when I verify, I'm letting StatCrunch do all of the calculations, and all I have to plug in is the degrees of freedom of 11, and actually I don't even have to plug that in. All I have to do is choose this data set, which is in your Unit 5 data sets, so I don't even have to do anything. I just have to choose a one sample hypothesis test in the T, and notice, yay, I get the same answer. So I would always do that, and if something is wrong, if those two don't match up, don't just submit it anyway, go back and check your work. My conclusion, and again I cheated a little bit because I used my interval that I found on my last video, so if you didn't watch that video, go back and watch it to see where those numbers came from. But a full conclusion says, given the high p-value of 0.238, we fail to reject the null. There is not strong evidence, or there is insufficient evidence, however you'd like to word it, that the mean lifespan of batteries exceeds 300 minutes. We are 95% confident that the true mean lifespan of batteries falls between 287.63 minutes and 324.87 minutes. This supports our conclusion to fail to reject the null since 300 falls in our interval. So that's the full conclusion using the confidence interval as well.